Hello, everybody. Um, I would like to thank you all for working on the homework assignment that I have posted, and your second homework assignment. Um, Basically, this homework assignment finishes up our prerequisite sections, and I just wanted everybody to be on the same page about networking, general networking ideologies and technologies, rather. And from this point on, we'll be focusing mostly on utilizing our socket server, electro server, to develop our projects. So here, this is a video that I would like to for everybody to listen to and to watch because it essentially answers the questions on the homework. So please listen to this video completely and try to understand the concepts. The homework grades will be available on the Blackboard as well. Let's start with the first question. The first question talks about the differences between the protocols that are developed to control the medium access layer, which essentially deals with it's a sublayer of your data link layer that governs the control of your physical layer, essentially controlling the network access. We want to talk about the advantages and disadvantages of these different protocols. The two protocols that are at question are round robin or time sharing strategies. So we've got our round robin strategies, and then we've got our time sharing strategies. Round robin strategies are basically token ring concept, or also some network technologies refer to that as token bus. And time sharing strategies are basically most famous. One of them is the Ethernet. It's basically governed by the time division multiplexing terminology, and it may also utilize the so-called collision detection and collision resolution mechanisms. So when the network access is controlled, when you have so in the round robin case, your network access basically goes with a ring to which all your devices are connected. So you've got the communication happening over a ring, and whenever a device requires to access the ring and to be able to send data over the ring topology, that device would have to listen to the passing by of a token. So if the token is and so you basically have a packet with a certain kinds of specifications, and this packet is basically going to be your token, and this token is going through from one device to another, and whenever a device needs to transmit, then that device would capture the token, and this basically represents the network being busy. So all these other devices will not be able to access the network. So this is going to be your network state. And then the device will take control of the network, send the information wherever it needs to go, and once it's done, then it releases the token. So when the token is released back, when the token is released back, then the state of your network will change from busy to open. And then so the network then the token goes from one device to another, and basically goes through the network until another device requires the token, so or the passing of the data. So then this third device will take the token, and then it will change the state back to busy, and then it transmits its data. So this is basically what is going on with your round robin connection. The next mechanism for controlling your network is basically through time sharing. And with this time sharing, some technologies would call it basically time division multiplexing. Or you may be able to look at it as a frequency division multiplexing, or FDM. So it's basically short for frequency division multiplexing. So the way that the multiplexing works is that if you've got a bunch of devices on the network, so and Ethernet basically, actually let me talk about this. This is 802.5. The standardization of token ring is basically IEEE 802.5, and the time sharing strategy or Ethernet is your IEEE 802.3. And there's subsets of standardization for all these devices, all these technologies. So in the time sharing, the way that your network is controlled, or your LAN access is controlled, there's going to be a centralized mechanism that takes care of reserving your network access. So if you think of the network access as being a time band, basically, your reservation will give each device a share of the network access. So you can split it into T1, T2, T3, T4, T sub 5, T sub 6. Here we have 4 devices, so let's go from 1, 2, 3, and 4, and then back to 1, 2, 3, and 4. So T sub 1, T sub 2, T sub 3, T sub 4. So the device number 1 will be able to utilize T sub 1 divisions of the time. So if the device has data to send, then this device would be able to send its packets when the time is being allocated to it. The device number 2 will be only able to send its packets and the information over the T sub 2 allocated times for it. And if it doesn't have information or packets to transmit, it's basically not going to utilize the network at that point. And then device 3 is going to utilize the sub 3s, and device 4 will be able to utilize its own time allocated spans. So basically this is the background representation of these 2 different technologies. Token ring is a technology. IEEE 8.2 is basically token ring, and then IEEE 802.3 is your Ethernet. Okay. So the advantages of round robin over time sharing strategies. With the round robin, as you can see, the network access is not limited per a specific time allocated. So first, in round robin, the biggest advantage for this is that you do not need a central time sharing mechanism. So all the devices would basically act with the same kinds of access to the network, and they just listen to the network to see if the network is free or not. And if it is free, they transmit their data. If it's not, they won't. Whereas in your Ethernet or time sharing mechanisms, you do need, so Ethernet needs centralization, basically to control the network access. In the token ring, you may have the possibility of collisions when that very same time that the token is being captured, another device may also listen to the network, and depending on the configuration, it might detect an open state for the network, and multiple devices may take. So the disadvantage here is that your multiple devices may sense the open state, and that causes for collisions, possibilities of collision happening. Whereas in time sharing, the mechanism basically uses carrier sense multiplexing, time division multiplexing, or CSDM with collision detection. That takes care of the less possibilities of collision. So your Ethernet advantage, so Ethernet disadvantage is it needs centralization. Robin's advantage is that it does not need centralization. Ethernet, through the carrier sense multiplexing, you will have less collision possibilities. Whereas, so this is the advantage for Ethernet. Actually, let me just do this with color codes. So, time division multiplexing, no collision, no centralization. CDMA requires centralization, so CDMA has no collision, whereas token ring is more subject to collision issues. Okay. When does token ring outperform Ethernet? When you have a lot of devices on your network, you'd outperform Ethernet because the time slots that you need to be allocating to your devices will have essentially will not limit the access to the network. So whenever the network is not being accessed, then devices will have the same priority and access to the network. What would be more useful for transmitting video or audio data? The Ethernet is going to be more useful for that because with video or audio data, you can packetize the data and then transmit them so that you would guarantee that certain device will have a regular access to your network, whereas with CDMA, with round-robin token ring, if a device decides to transmit the video data, then they would be occupying the network, for long periods of time. And finally, the question, so this is question number 1. And finally, the question is asking about what is the frequency division multiplexing. Frequency division multiplexing works pretty much like time division multiplexing, and the difference between frequency division multiplexing (FDMA) and time division multiplexing or TDMA is that in time division multiplexing you have the time, and then you divide it. So device number 1 can access at a certain location in time, at a certain point in time, device number 2 and device number 3 and device number 4, and so forth. With frequency division multiplexing, you basically access or multiplex your bandwidth over the frequency. So you will be able to allow device number 1 to access for a certain range of frequency and device number 2 to access a certain other range of frequency, and so on and so forth. This basically is like the radar technologies and the wireless technologies. For example, if you've got like a police station, and then you've got your hospital, and then you've got your radio station, they're accessing the same band, the electromagnetic bandwidth, and each of those are given a certain frequency range. So for example, your police station frequency range is basically, say, it's from 1 kilohertz to like 3 kilohertz. And then you give your radio station from 100 kilohertz to 200 kilohertz. So this way, basically what they need to do is that for their signal, they would send their signal over a certain range of frequency, and that way they would be able to send the data all the time, making sure that their data is not colliding with the other radio stations and with the other stations. So frequency division multiplexing splits these or makes these reservations not in the time domain, but rather in the frequency domain, so that whenever you're splitting your data, any data that's within this frequency band is going to be for your police station, and any data that's in this other frequency band is going to be with your radio station or whatnot. So so the difference or the frequency division multiplexing works this way. If you want to think about probably the most obvious example of frequency division multiplexing, FDMA, it's basically your DSL line, or rather here we call it asynchronous digital subscription line. So what that does is that when you say call up AT&T and get a broadband internet access with the ADSL, what they do is that they utilize your telephone line, so your physical layer is basically your telephone line, and then they multiplex your voice and your data over different frequencies. And usually voice goes into lower frequencies, so so voice communication is going to be at low frequencies, whereas your data communication goes at a higher frequency. So that way you will be able to utilize, for example, 3 megabits per second for your DSL data line, and then for your voice you're basically looking at 56 kilobits per second for voice communication. So that's basically how frequency division multiplexing works. So you will get both your voice and your data packets on the same line, but you would basically apply a low pass filter to get the voice data and a high pass filter to get your data. All right, now let's talk about question number 2. And this question is asking 1, 2, 3, 4, 5, 6 true-false questions, and I'm going to label them as 1, 2, 3, 4, 5, and 6. And we'll go over the answers to these questions. They're basically true-false questions. Question number 1 asks and says, the connection-oriented network are capable of doing better flow control compared to the connection-less networks. This statement is true, and the reason for that is in connection-oriented networks, you will have the source and destination locations, or rather addresses for the packets and the frames that are being delivered, associated and identified. And also you can guarantee the in-order delivery of your packets at the destination, because each packet or each frame will get a time frame as well. So for this reason, you will be able to implement complicated flow control mechanisms based on the packet orders, packet delivery mechanisms, and so forth. Whereas with the connection-less networks, you will not be able to do that. So your flow control is going to be rather limited in that sense. The second question says that TCP is a better protocol for real-time multimedia transfer compared with UDP. This statement is false, and the reason for this is because in the UDP protocol, you do not need, it's basically connectionless. And connectionless protocols are better for real time, or rather better for media delivery. The reason for this is, when you're watching a real-time video, if the packets are out of order or they're not really coming through as you expected, you will be able to tolerate the missing packets for the sake of the synchronicity of your network or your media applications. Whereas if you do that over TCP, if a packet is lost, then the future packets would have to wait until the packet is resent and re-received. And for this purpose, you will not be able to utilize it for media applications. In fact, the connectionless protocols are preferred for media. For media applications. Okay. Question number 3 says that in the OSI model, the most consistent and complete levels of agreement found among network manufacturers should be in the transport and network layers. Well, OSI is actually, I would classify this statement as false, as it's a bit vague, but still, if you think about the OSI model, the network layer and transport layer are already standardized, but then they would allow for, so the network layer and transport layer these basically allow for interoperability. Within your network architecture, so there's not much standardization here. Basically, to be able to allow this, you would need to have less standardization and more control, rather more flexibility. Connectionless networks are preferred for real-time multimedia. This is true. Basically, this backs to the question number 2. So question number 2 and question number 4 are kind of sort of saying the same thing differently. But connectionless networks are better for real-time multimedia applications because there's there's not much strict relationship between the sending and the receiving of the data. So if anything is lost, your data is not going to be held up. Question 5 says, in connection-oriented networks, the number of total bytes transferred is less than that of connectionless networks. This statement is also false, because with connectionless networks, you have less overhead. And this is because there is less strict rules over data delivery. Whereas for connection-oriented, you need more overhead, which basically makes for better control with the price of size. And finally, pay-per-view on cable television is a multicast. This is true because multicast transmits to a group, whereas broadcast transmits to all users. So this is a multicast is in pay-per-view, and the statement is true. Okay, question number 3 asks about the QoS, or the quality of service for your network. The answer to this question is pretty much straightforward. It should come from the text, the text that I uploaded as the additional readings, pages 352 all the way to 356. Talk about different levels of quality of service. What does quality of service mean? So this basically refers to QoS. What does the quality of service means? Quality of service is a means, is a mechanism for traffic shaping. The 3 levels of quality of service, so you've got 3 levels that are discussed in the textbook, and this question basically asks for those. You've got your best effort quality of service, and you've got your differentiated service, and then you've got your guaranteed service. The best effort basically is like a first in, first out queue. The differentiated service is a priority queue. And your guaranteed service, or a hard QoS, is basically a custom queue. Multimedia communication and video, or rather video on demand and teleconferencing. The video on demand You need to have a guaranteed service because the users are paying for the video, and so they need to get the packets that they're requiring are going to be having to be more stringent in terms of their delivery. In the teleconferencing, since it's a real-time application, it could even do with the best effort. So the users need to get the packets if they can. But packet loss is tolerable for the sake of speed. Question number 4. Transmission error is common in network communication. What is error rate and how is it measured? Mention why error occurs. Basically, error rate, we can consider this as the percentage of correctly received packets over the total sent packets. Okay, so and this, we usually consider this as a percentage of the total number of packets received. Why does error occur? The reasons are basically, you can think of dropped packets, erroneous reception, media noise, traffic, and congestion. Etc. How does receiver detect error? On the receiver side, compared to the sender side, when the sender sends a bunch of packets to the receiver in, say, connection oriented packets, the packets may be labeled. So when the receiver receives the packets, then it will be able to kind of detect how many packets it's receiving and how many packets are out of order and so forth. So these will be able to, will make the receiver able to send and detect how many packets it's received out of the total number of packets that it needed to receive and calculate the error rate. How does the sender detect error rates? If the receiver sends acknowledgments versus not acknowledgement signals, then the sender will be able to calculate how many packets were received at the receiver side and how many were not. Also, the sender may be able to inquire or send packets in terms of inquiring the number of packets that the receiver had sent and compare them with the number of packets it sent to be able to calculate its error rates. This also answers the question about connection oriented networks versus connectionless networks. So connection oriented is easy because you can have the packet numbers, you can have packet orders. In connectionless networks, you won't be able to receive the packets or detect the packets order of delivery. You can actually create CDC, cyclic redundancy, or rather CRC checks. Maybe you can add error detection patterns. And so forth to be able to detect errors at both the sender and the receiver side. Alright, now let's take a look at question number 5. So in question number 5, we're basically looking at routing data, and we'd like to see how this is achieved by setting up connections between sender and receiver in a connectionless manner. The main differences between, so first let's look at connectionless versus connection oriented. Networks and protocols. In a connection-oriented network protocol, you've got your sender and receiver, and what you're going to do is that you're going to establish a connection between the two. So the sender would receive connection information, and then the line will be reserved, and an acknowledgement would be sent back to the sender. So I'll have S and R. This includes the data route and other factors that they need to be established prior to your transmission. And while the two devices are connected, the route will remain open for all the incoming data to be sent through it. In a connectionless medium, basically your sender, all it requires to have is the establishing of a specific, an implicit route to the receiver. So this implicit route could be through this black route, or it could be through this other route. Or it could be through. So as long as there is a route between your sender and receiver, the connectionless protocols will be able to transmit the data. So no specific route needs to be completely established. This allows for out of order delivery for connectionless networks of your data packets, whereas in a connection-oriented packet, you guarantee in-order delivery. In-order delivery of the packets. How is a packet delivery achieved in these two cases? In both of these protocols, you transmit your data through the medium to the server with with the connection-oriented, the data will be sent through a reserved route, whereas with the connection less delivery, the data will be sent with a destination packet, and then the routers in between will try to figure out the mechanism or the route to forward the packet to the destination. Give an example of protocols used in the industry for both these cases. So TCP is a perfect example of connection-oriented, whereas UDP or user datagram or universal datagram protocol and IP, Internet Protocol, are the protocols for connectionless industry standards. Which is more reliable? And to give an example, basically, in terms of the reliability, it depends on what we're talking about. In connection-oriented, well, connection-oriented is more reliable. So basically, check the connection-oriented in this case, because with the connection-oriented delivery, you reserve a route, then you tag your packets and a timestamp for them to be delivered. And if a packet is not received properly at the receiver end, due to so if packet is not received, if packet is lost, you'll be able to resend with connection oriented. In connectionless delivery, you're not really that much concerned with your packet loss. So in connectionless, if packet is lost, you won't resend it. Which type is usually used for real-time applications? So for real-time, we use connectionless mechanism. The reason is because we are more concerned with the real-time constraint rather than packet loss. Okay. Which one is better for control network flow? The connectionless is better. Connection-oriented is better for control flow. So this is question number 5. Alright, now let's look at question number 6. Network congestion refers to a state when a network throughput goes down due to multiple senders on a network simultaneously sending data. What it means by network, what is meant by network congestion, and how does leaky bucket protocol try to control it? Network congestion basically means when you have multiple devices on the network that are sending data at their maximum rate. At some point, the addition or the accumulation of all the packets that all these devices are creating will exceed the capacity of your network. You can think of this as, for example, a highway. So let's suppose that we have a highway and a bunch of different ramps that are joining essentially traffic into our highway. So this is basically, got my main highway going in, and then I've got a bunch of streets pouring traffic into this highway. So you can think of these as my devices essentially adding traffic to the network. So if I allow these devices to enter packets into the network, so this device is basically sending packets through the network. So these red packets are coming in, right? And then they're traveling through the network. Then I'm going to have this blue device also send packets to the network. So blue packets are coming in, right? And then I've got some, say, green packets being added to the network. So as you can see, at some point, my network is going to be flooded by all these different units, essentially, trying to add to my network traffic. So at some point, the network will be overloaded by the amount of packets that are traveling through it. So you're going to have congestion. Now, how does leaky bucket addresses this issue? Leaky bucket basically works like the red lights that you have at the traffic ramps, right? So it basically, what it does is that if network is congested, it basically stops traffic from entering your network. So for example, if you had a little red light, let me just try to put the red lights at each of these entry points, right? So when your network is congested, then the leaky bucket basically holds on to the incoming traffic. Okay, so it cuts the traffic out until the network is available to pass data, and then it would allow one packet per blink of a green light to enter the network, basically causing a steady rate of packets entering your network. So that's basically what the leaky bucket does. The way that you want to look at it is that think of it as this way. You've got a funnel, basically a bucket with some capacity, and all of your network devices are connected to it. Okay, so I've got a bunch of these devices connected to the bucket. The bucket has a little hole at the very end of it, and then it enters into your network flow. So what you're going to have is that here you're going to have M, which is going to be your throughput. For your network. This is usually in megabits per second or Mbps. And then you've got your devices that are adding packets at a certain rate. So each of these are going to have, call them R sub I, the rate at which they are adding packets to your network. When these packets are being arrived inside the leaky bucket, so this is going to be your leaky bucket, they're going to basically accumulate inside this packet, this bucket, okay? And then the bucket will have a steady state rate, and I will call this with this blue line, I'll call this my steady state rate, and let's call this S, basically the leak rate. This is going to be also megabits per second. How many packets, how many bits it allows entering the network. So if these data, the sum of all these R sub i's, is less than the steady state rate, and it's going to basically inject the packet as soon as it arrives. Once your packet rates start increasing, then the packets would have to wait for them to be able to enter in the traffic, because your bucket does not allow more packets go out of it than they are coming in. So it have essentially a packet accumulation with leaky bucket. So that's how leaky bucket operates. So this is basically the operation of leaky bucket. Now the next question is, when this protocol is used, when you're using leaky bucket, let's calculate some basic stuff about your network congestion. A computer has a maximum packet size of 1000 bytes per second. So if you've got a computer with a maximum packet size, so let's call this packet size equals 1000 bytes. So if you have a packet, this packet is going to be 1000 bytes long. And then it's basically entering the leaky bucket with a little leak at the end of it. Entering your network, traffic to your network. Okay. And your computer also produces at the rate R sub I of 10 million, 10 times 10 to the 6 bytes per second data that's coming inside your network. The bucket size, so the bucket size is 1 million bytes, 10 to the 6 million bytes. The question is how long can a burst at maximum speed last? Now notice here the maximum speed, I forgot about the network traffic, and your network throughput, basically the speed of your network is 10 million. It's 50 million. 5 times 10 megabits, megabytes per second. So your speed is 10 Mbps. Your outgoing rate or your traffic is 50 Mbps, and your bucket size is 1 million bytes, which is basically 1 million bytes. Now, the one thing that in this calculation doesn't matter is the size of the packet, because we're calculating everything in terms of bytes per second, million bytes per second, million bytes per second, and million bytes here. So we don't really need to have the packet size. So we're not going to use the packet size in this case. So let's just kind of sort of not worry about that. Now, look at your outgoing rate. Your outgoing rate is equal to M, which is 50 megabytes per second. Your incoming rate is equal to R sub 1, let's call this R sub 1, and this is going to be 10 megabytes per second. Since R sub 1 is less than M, therefore you would have no congestion, which means that there's no need for the bucket. So the bucket will not fill. So the packets, all the packets that are coming in, their incoming rate is much less than the outgoing rate of these when they enter the traffic. So every single packet that arrives is going to be added to your traffic. And so the maximum burst time is going to be indefinite. So the maximum T burst is going to be infinity. Now, if you had multiple computers connected to this leaky bucket, the sum of the incoming rate would have been more than the amount that your traffic could handle, or essentially how much your bucket will leak inside the traffic pattern, and you would be able to calculate some T-burst from there. Now, if you had looked at this question and you had considered, instead of the R sub I, the amount that is produced by your computer, if you consider that as the steady rate, right? So if we had S to be 10 megabytes per second, then you would be able to calculate the burst as being equal to the size of your bucket divided by M minus R. So your size of your bucket is 1 megabytes, and then the difference would have been 50 minus 10 megabytes per second, which would give you 1 over 40 seconds, which would be 5 milliseconds. Which would be 25 milliseconds. And that would be how much time it takes for the traffic to get regulated. Okay, so either one of these two answers, the 25 millisecond or infinite burst, I accept. It depends on, the question was not quite clear as to whether that 10 megabits per second was the speed at which your bucket introduces net packets to the network, or speed at which is added to the bucket. And for this reason, I'll consider both of these answers as correct answers. All right. Question number 7. Question number 7 talks about a token bucket scheme that limits the length of the traffic burst that can enter into the network. In the token bucket, as opposed to the leaky bucket basically had a steady outgoing rate that it would inject traffic into your network. In the token bucket, it allows for a certain amount of bursty traffic by looking at or adding a bucket every t milliseconds or every t seconds, and by adding the bucket, the tokens to the bucket, it basically accumulates how fast packets would be able to get introduced to the network. In this case, you've got M, which is going to be your truth worth of your network. It's basically how fast, how many packets per second, how many bytes per second, how many bits per second your traffic, your network can handle. It's the bandwidth of your network. Then R is the the incoming traffic. You can consider this incoming or steady state or steady rate of traffic being added to the network. And C is the size of your bucket. So C is basically equals the number of tokens that the bucket can hold. Okay, so if the bucket is full, which means that, so if bucket is full, which means that you have C packets, then all of these packets will be able to be injected inside the traffic, which means that the traffic will last for m minus r which is actually effective traffic rate. Effective traffic rate is going to be m minus r, the amount that the network can handle, minus the amount that is added to it. And so so the size can be sent is going to be m minus r over c. It's going to be the total size of the burst, and therefore the time of burst is going to be 1 over size of burst, which essentially the time burst is going to be size of your bucket over the effective rate. Okay, so this answers the first question. The first question goes, if you have the token arrival rate, so your token arrival rate is going to be 4 megabytes per second. So it's going to be 4 megabytes per second. And then the output rate, M, is 32 megabits per second. Notice this is bits, this is bytes, right? So we're going to get into this. And then it says, what is the bucket capacity that allows for 10 millisecond burst? One of the things we need to do here is to first turn the 4 megabytes into 4 megabits. So this is going to be 4 times 8 megabits per second, which is going to be 32 megabits per second. Now from this equation, let's call this equation number 1. So from equation number 1, we know that the time of burst is going to be C over m minus r. We know that time of burst is 10 millisecond. So 10 millisecond is going to be C over m minus r. Okay, now we know what m is. M is 32 megabits per second, and R is 32 megabits per second. So we've got 32 minus 32 megabits per second, and C is the size of the bucket. Okay, now from here, what I'm going to do to get the size of the bucket, C is going to be T burst times m minus r, which is going to be 10 millisecond, just 10 to the power negative 3, times 32 minus 32 times 10 to the power 6. So this is going to be 10 negative 2. This is going to be 10 to the 6. Multiplying these two is going to be 3200 times 10 to the 4, which is going to be 32 times 10 to the 6, which is going to be 32 megabits. So size of the bucket is going to be 32 megabits, which means that it's going to be, if you divide it by 8 megabytes, which is 4 megabytes. So from here, the size of the bucket is 4 million bytes. Second part of the question says, using this bucket capacity that we computed, how long it would take to send 201000 bytes of data when the bucket is half full. Now, 25% full. So let me just erase these upper parts. Let me just save this. 32 megabits. Alright, so now if the bucket is 25% full, let's see what happens. This is my bucket, okay? And it's adding traffic to the network. If the bucket is 25% full, when the network traffic comes in, that many bytes of it are going to be directly sent inside the T burst, right? And then the rest of the traffic is going to be added at a steady state rate. So when C is 4 megabytes, then 25% of C is going to be 4 megabytes divided by 4, which is going to be 1 megabyte, right? So at first, with 25% of bucket full, then 1 megabyte of data is transferred immediately. Okay, then the rest of the data will be transferred at the steady state rate. So you have 1000, which is 2.01 megabytes originally. From here, 1 megabyte is sent, so add 1 megabytes per second, so you've got 2.01 minus 1 megabytes left, which is going to be 1.01 megabytes. Your steady state rate is 4 megabytes, so your steady state is 4 megabytes per second. Therefore, the time it takes is going to be 1.01 over 4 seconds, which is going to be 252.5 milliseconds. This is how much it takes for your data to be sent. Now, to calculate it completely correctly, what you would have to do is that you know that 1 megabyte of your data is sent at 32 megabit per second, which is equal to 404, 404, 404 megabyte, and then 1.01 megabyte of your data is sent at 4 megabytes. So the time here, t sub 1 is megabyte per second. This is megabyte per second. So the time t sub 1 is going to be 1 over 404, and the time sub 2 is going to be 1.01. Okay, so this is going to be this much second, and this is going to be 1.01 per second. So the t sub 1 is going to be 2.5 millisecond, and t sub 2 is going to be 252.5 millisecond. When you add these two, the total t is going to be t sub 1 plus t sub 2, which is going to be 254.9 milliseconds. So the accurate calculation of sending that much bytes is going to be this. So any number 252.5 or 254.9 or rather 255 are sufficient for me. So again, the final answers are going to be either 252.5 or, so it's approximate, or 255 millisecond. Both of these answers are acceptable. Alright, question number 8. In question number 8, it wants to compare connection-less versus connection-oriented packets, routing mechanisms, or connection-less versus connection-oriented protocols. And it supposes that you've got two different systems. One system is a connection-less protocol. Basically, computer A is connected through the cloud in a connection-oriented, connectionless mechanism to your destination. So we call this connectionless. And then computer B uses 5 switches or rather 5 hops with 4 switches to connect to the destination. And then it supposes that the switch lengths, basically the speeds, I call these L, so the speeds of each link, L sub 1, L sub 2, L sub 3, and L sub 4, sorry, sub 3, sub 4, and L sub 5. So L sub 1, 2, 3, 4, and 5 is 1 megabits per second. So this is your speed, 1 megabit per second. And let's suppose that all of the links in the connection-oriented, connectionless mechanisms are also 1 megabit per second. Okay, so this scheme is the connection-oriented, and the scheme A is connectionless. We have two situations. Situation number 1 when we are using a video file and its size is equal to 1 megabits, and we want to send this file as a whole, and we want to test the speed or the time delay between when the file is sent and it is received. If we look at the connectionless mechanism, we're sending a file with the size of 1 megabits per second, a file with the size of 1 megabits, and we want to send it over to the network that can handle 1 megabits per second. So the time that it takes is going to be 1 megabits, the size of the file, over 1 megabits per second, which is going to be 1 second. So it takes 1 second to send the file in a connectionless manner. With the connection-oriented manner, the file is sent from the source B, and it goes from source B, now draw this with red lines, and to each of these intermediate switches, and then it's going to arrive at the destination. So if my file size is if the file size is equal to 1 megabits, and over the link sub 1 at 1 megabits per second, it takes t sub 1 equal 1 second to send to intermediate switch L sub 1. Same with L sub 2, L sub 3, L sub 4, and L sub 1. So it takes 1 second here, 1 second here, 1 second here, 1 second here, and 1 second here. So therefore, at L sub 2, L sub 3, L sub 4, and L sub 5, all of these are going to take the same amount of time. Basically, each of these we're going to take T sub 2, T sub 3, T sub 4, and T sub 5. All of these are going to be 1 second. So in total, the time is going to be the sum of T sub I being 1 to 5, which is going to be 5 seconds. This is case 1. So for connection oriented, it's going to take 5 seconds. For connectionless, it's going to take 1 second. If we break the file, instead of 1 megabits, if we break it into packets, 10 packets, and each of these packets are going to be essentially 100 kilobits. Okay, so we've got 1, 2, 3, and so forth to 10 packets. When we send these packets over the connectionless network, the first packet takes 1 millisecond to be sent by some route. The second packet takes 1 millisecond, goes over 1 megabit per second over some route, and so on and so forth. And so if we calculate these, basically packet number 1 might go through this route, packet number 2 might go through this other route, packet number 3 might go through this other route, packet number 4 might go through this other route. And so if we consider these each to take 0.1 second, then in total, the total time that it takes over the connectionless protocol is going to be in total 0.1 second. Okay. Now, if we consider that these also have 5 hops, then with hops, this is going to be 5 seconds, and this is going to be 0.5 seconds. Okay. Now let's look and see what happens with the connectionless or connection oriented. So with connection oriented, if I break my my message into 10 packets, and then each of these packets are 0.1 megabit, 100 kilobits per second, then each packet, so at L1, L2, L3, and so forth, each packet takes 0.1 second. So then in total, the sum of t sub 1 to t sub 5 for each packet is going to be 0.5 seconds. But this is just for each packet, right? So this is for each packet. Now the problem is that I have 10 packets, so therefore still the t is going to be 10 times 0.5, which is going to take 5 seconds. So the point of the question is that with connection oriented, the time doesn't matter. With connection oriented, with large or small packets, time is invariant. And that's the difference between connection oriented and connectionless. So finally, question number 9 is asking, what is the QoS and what is it measured? So it's basically a measure of traffic control. And the measures that we have with the traffic control was basically the latency or delay, your error, and your throughput are the measures that your QoS is basically tries to implement and improve. So just refer to your textbook and derive measurements that implementation of different QoS mechanisms, best effort, guaranteed service, and differentiated service, and how they reach it. How can QoS be effectively implemented for large band networks? Time division multiplexing, frequency division multiplexing are basically the ideas that you can have implemented. You can have higher frequencies applied to high priority applications and high priority signals, so you would be able to send them faster and quicker, and lower frequencies for lower priority signals. You can also implement them through priority queues or custom-made priority queues. Now you can do that in the narrowband networks. You wouldn't in narrowband networks. You wouldn't be able to do the frequency division multiplexing. So you would have to come up with alternative approaches, and most of them would be done on the application side of the process. So this is basically the answers for the second homework, and from this point on we will be going to implementing our projects on our socket server, the Electro server. Thanks again for listening, and I hope that these answers clarified some of the questions you may have had about the second homework, and I will talk to you for the rest of the class in our videos that I will post either on a weekly basis or on a bi-weekly basis, depending on how much coverage are given to a certain units of the class from this point on. Thank you so much and have a good evening or day depending on when you're watching this video.